Well, thank you all so much for joining us for Why is the Earth Getting Both Wetter and Drier? The Science of Climate Change. Parts of planet Earth are getting wetter while other parts are getting drier. Many places, including New England, are experiencing extended dry periods and then suddenly receiving a 1 in 1,000 year flood. So we're going to examine the science of climate change and why it is driving both wetter and drier conditions. And we're going to explore how the climate is changing in New England and what the future may hold. And this is all led by Stephen Young, Ph.D., Professor of Geography and Sustainability Department at Salem University. So all 130 of us who are watching live and the many more that will watch the recording, let's give a big virtual round of applause for Professor Young. And Professor Young, you can take it away. Thanks so much.
Well, good evening. And Robert, just let me know if my voice goes out or anything like that. And I do apologize for not having the camera working. Not sure why. I haven't used the laptop in about 2 months, and so could be an issue with Zoom. Anyway, you get to see a picture my son drew when he was 14 years old of me at a birthday party, and so it's pretty close looking. And maybe I am saving you from seeing my face. Anyway, welcome to the talk tonight. Why is the Earth getting wetter and drier? And by the end of this talk, you will be able to answer that question yourself, hopefully. And so a little bit about myself. I am a professor of geography in the Geography and Sustainability Department at Salem State University. My area of expertise is looking at the Earth from space, from satellites, from drones, from airplanes, and understanding how the Earth is changing. I'm focused these days on climate change, on temperature, on snow cover, and so that's a little bit about me. So let me do this. So first, I would like to extend thanks to Robert Hayes, who just spoke. He's the Community Outreach Librarian and Head of Technical Services at the Tewksbury Public Library. And thanks to the Tewksbury Public Library and the other libraries and organizations that have made tonight possible, and to all of you for joining us tonight. So tonight's program, I'm going to talk about the science of why our climate is changing and how it affects the water cycle, how it's making the world wetter and drier. Then I'm going to talk about some changes happening in New England, a little bit about our future. And I teach a semester-long class, and at the end of the semester, I still feel like I haven't gotten it all across. So this is a Cliff Note edition of what's happening. I can always go in more detail in questions. All right. So we live in this amazing world, an incredibly complex world, and one way that we can understand it is through science. And so what is science? It's a method. It's a way to understand the world. It's based on observations. And I highlight based on observations because tonight I'm mostly going to show you observations and data, and you can interpret what's going to happen in the future once you understand these observations. Science is completely transparent. There's no secret recipe, no secret handshake. We constantly are doing experiments to see under different conditions if things are true or not, and it's ongoing. It's always refreshing itself. And we've got all kinds of instruments out there to measure the atmosphere, to measure the temperature, the wind speed, the humidity, not just from these ground instruments, but I use satellites, and satellites can measure so many different aspects of our atmosphere and the surface of the Earth. And these ocean buoys are incredible. Sometimes it's amazing the ingenuity of humanity. And I think this is an incredible way for us to understand our world and get data. So we've got thousands of these buoys out in the ocean. And what they do is they descend into the ocean. And as they're descending into the ocean, they're taking temperature, salinity, different information. And then they park themselves at about 1,000 meters below sea level, and they stay there for about 9 days. Then they descend down to 2,000 meters, collecting data the whole time, and then they pop up. They send all that data to a satellite. That satellite sends it to a receiving station, and then scientists look at that data and organize that data. And so we, through these instruments, we have a really clear understanding of what's happening on Earth. And this is a result. This is a result of those land instruments, the temperature instruments, and the temperature instruments in the oceans. And so this is a graph of global average temperature from 1850 to 2024. And we're going to spend a little bit of time on this graph. First, along the bottom of the graph are the years. And on the far right, it begins at 2024 and goes all the way back to 1850. On the right-hand side are what we call temperature anomalies. Temperatures of how far that year has swayed from an average year. So anomaly, right? Every one of those black dots is an annual temperature anomaly. And what that means, an anomaly is something that's different. And it is different from an average temperature. So in the gold box, you should see global temperature anomalies are relative to 1850 to 1900. So on the far left of the graph there, we take the annual temperature of 1850 all the way up to 1900. We add them together and divide by 51, and that gives us the average temperature for that period from 1850 to 1900. And then each of those black dots is how far that year's temperature varied from that average. And the reason why we choose this area is because that is what we consider pre-industrial. It's before we put a lot of carbon dioxide into our atmosphere. It's the closest we can get to a period before a lot of pollution where we have data. So I want to reiterate, an anomaly is how far that year's average temperature varied from the average of 1850 to 1900. And we can see that up in the far right, that's last year's anomaly. That's how far last year was from the average temperature before 1900. So this really helps. This black line is the average of that golden box over here on the left. And so every dot that's above that black line is warmer than that long-term average, and every dot that's below it was colder than that long-term average. And in this case, I've highlighted this one dot here. I think it's like 1918 or 17, and that was 0.2 degrees Celsius colder than that long-term average of 1850 to 1900. The two golden annual anomalies were warmer than that long-term average. And notice that tends to go up and down, up and down, up and down, up and down, up and down. It's because the Earth is very complex, and energy is constantly moving around. And so some years we've got an El Nino, and energy is being released from the ocean to the atmosphere. Some years it's a La Nina, and energy is being consumed by the ocean. So that's why we get that up and down variation. In the middle, that red line is what we call a running average. Because each year is up and down, up and down, up and down, you can kind of get a sense of how things are traveling. But here, we take 5 of those years and average them, and then we take a new year and we add it to the 5 and drop the oldest year, and then we move it along and we add the newest year and drop the oldest year. And it gives us that smoothing, and we can see the broad pattern that's happening with annual temperature. So here's an important thing about science. We always say what we don't know as well as what we know. And these black lines, they're vertical lines, they go up and down, and it's called the confidence interval. And what it means is that black dot is what we think is the best average for that year. However, it could be anywhere along this black line. There's a 95% chance that it's anywhere on that line, but it's probably there in the middle. And back in the early 1800s, we did not have a lot of thermometers around the world, so we have a little bit more margin of error. If you notice, more recently, there's very little margin of error, right? We've got all those buoys out in the ocean. We've got lots of thermometers around the world. So we have a very good, not a lot of uncertainty in our current temperatures. So what this graph shows us, right? So again, I want to reiterate that that black line is the average global temperature for this 51-year period. And everything above that black line has been warmer than that long-term average. And the last year to be colder than that average was 1935, 90 years ago. So for the past 90 years, we have not had a year that's been colder than the pre-1900 average. And as we see from the running average, it really is increasing. This black box here shows us in the 60s, 70s era. This is where I think things really changed. So we've got the annual anomalies going up and down, up and down, up and down, up and down, and they're starting to move above this black line, the base period. But it really is not until the mid-70s that we see the long-term running average really turn up, and it hasn't changed course since then. And the main characteristic of our new climate is that we are in a period of continual warming. It may vary a little bit from year to year, but we are continuing to warm. That's the key takeaway. And that is based on those observations. So this is a scientific graph, typical graph of how we present our information. So let's look at temperature over a longer period of time. We went back to 1850. There are ways, they're called climate proxies, and I'm going to talk about those in a little bit, but there are ways to find temperature data of in the past. NH means Northern Hemisphere, so a lot of these data sets are the Northern Hemisphere. In fact, there's just only one that's global. But although they're not exactly with each other, they're pretty similar to each other. And so the red over on the right is actual measurements of our atmospheric temperature. And we can see that the red line, the current thermometer temperature readings is that we haven't been this warm in a long time. This graph goes back to the year 0, right, when Christ was born. And this graph is a little old. In fact, that's where we are right now with temperature relative to temperature over the past 2,000 years. We are literally off the graph currently. So the reason why the Earth is the temperature that it is we get incoming solar radiation from the sun, and we send thermal energy out to space. And when temperature stays the same, we get an equal amount of incoming energy versus outgoing energy. Every object that has any energy content is radiating, is losing energy. And so the Earth is losing energy out to space. And that's how we maintain our same temperature. So we saw that the Earth's temperature is increasing. And it's not because we're receiving more energy from the sun. And so here's a graph, and the yellow line is the smoothing of incoming solar radiation. And it goes from 1880 up to about 2018. And the red is the smooth line of the global temperature rising up. And so there is not a relationship currently between incoming solar radiation and our rising temperature. What's happened is we've changed the chemistry of our atmosphere, and we've put these greenhouse gases into the atmosphere. And what they do, they act like the glass of a greenhouse. They let the incoming solar radiation pass through the atmosphere. That radiation strikes the Earth. Some of it reflects back to space, and some of it gets absorbed and turned into heat energy by the Earth's surface. And then the Earth sends radiation back out to space. And we're cooler than the sun, so we send out this long wave thermal energy. And just like the glass of a greenhouse that stops hot air from leaving, the gases like carbon dioxide absorb the thermal long wave radiation and radiate some back to Earth, making Earth warmer than it would otherwise be. I do a whole week on the greenhouse effect, so I'm not going to go more details, but that is why we're heating up. Is not getting more incoming energy, but we're sending less energy out to space. It's like a bathtub. If the amount of water going into that bathtub equals the amount of water that's leaving the bathtub, that duct will stay in the middle of the bathtub. However, if we squeeze the drain pipe and we don't let out as much water as coming in, that bathtub is going to fill up with water. And that is exactly what we're doing. We're through putting greenhouse gases in our atmosphere, we are squeezing the outpipe for energy leaving the Earth. And the Earth is filling up with heat, just like the bathtub is filling up with water. And we can measure it. We've got satellites that are able to measure how much energy is leaving the Earth, and we have satellites that measure how much energy is coming from the sun. And one thing we do in science is we quantify things. And so here we've quantified how much energy is actually staying on Earth. Not to go into the details of this, just showing you. So where is all that heat energy going that the greenhouse effect is creating? Most of it's going into the oceans. That's why we really don't feel the effect as much. The oceans are like huge batteries. The oceans are vast. They cover over 71% of the surface of the Earth, and they're very deep. So they are filling up with energy, and we're starting to see some of those repercussions of that energy in the ocean. Only 2% goes in the atmosphere. That's why we're slow to really feel the effects of our warming. All right. I said earlier that we're going to talk about climate proxies, how we see things into the past. And one of the cool things in science is we've discovered that we can drill into ice cores in Antarctica and Greenland and find out what the temperature was like on Earth hundreds of thousands of years ago, and what the atmosphere was like. And what happens is here's an ice core that we dig out, and here's a slice of that ice core. What happens is snow lands in Antarctica every year, and it lands on Greenland, and the next year more snow lands, and the year after that more snow lands, and eventually the weight of the snow compresses that into ice, and we capture air bubbles from the atmosphere at that point in time. Also, there's a thing called oxygen isotope analysis where we can take oxygen molecules and determine what the temperature was like at that point in time as well. So we have this graph here. On the bottom right is today, and the time period goes back to 422,000 years ago. Carbon dioxide that we got in those air bubbles is in orange, and temperature that we got through the oxygen isotope analysis is in the purple. And one thing we see is that these two are very related to each other. When carbon dioxide goes up, temperature goes up. When carbon dioxide goes down, temperature goes down. And temperature also influences warmer air, influences more carbon dioxide to move into the atmosphere. Cooler atmosphere temperatures move carbon dioxide into the earth. So those two are related to each other. You can clearly see these patterns that go up and down, up and down. These are different glacial periods, and they're actually caused by the changing orbit and tilt of the Earth, called the Milankovitch cycles. And I'm not gonna get into those, but that's what's causing that change over these periods. But what I want you to get out of this graph is the relationship between carbon dioxide and temperature. And here we've got another one. This is from the Vostok station, the Russian research station in Antarctica, and we're going back 800,000 years. And in the brown is temperature in degrees Celsius, and on the top is carbon dioxide concentrations in what we call parts per million volume. And so again, as carbon dioxide rises, temperature rises. As carbon dioxide drops, temperature drops. And this graph is also a little old, and this is where the amount of carbon dioxide in our atmosphere is right now. Again, we are out of the ballpark on this. And in fact, I grabbed this graph from climate.nasa.gov, and this website is scheduled to be taken down with all the climate data. But that dotted line is the maximum level of carbon dioxide over the past 800,000 years. And you can see today we are well out of where we've been in the past. So we measure carbon dioxide in the atmosphere. And since 1958, we've been measuring how much carbon dioxide is in our atmosphere. And carbon dioxide in the atmosphere goes up in the wintertime and comes down in the summertime, because the northern hemisphere has a lot of land area in the northern hemisphere, and there's a lot of forest. And in the summer, the forests pull carbon dioxide out of the atmosphere, and then in the winter they put it back up. But the long-term trend, that running average, which is the black line, is the human added carbon dioxide to our atmosphere. And I grabbed this graph in May of 2025, about 2 months ago, and we continue to put carbon dioxide in the atmosphere. And methane, another greenhouse gas. Not gonna go into the details of that. So, review. We know that through lots of different experiments, not just ice cores, but lots of experimentation. We know that carbon dioxide is related to temperature. And we know from measuring our atmosphere that we continue to put more carbon dioxide into our atmosphere. And that carbon dioxide in the atmosphere is driving the global temperatures to be warmer and warmer. Each year is not warmer than the prior year, but every few years it jumps up. And so we get that moving average shows that we are in that warming trend. The next graph. This graph, if you understand this graph, you will be able to answer the question of why Earth is getting wetter and drier. Along the bottom is temperature in degrees Fahrenheit. Starts at 0 degrees Fahrenheit, which is below freezing, and goes up to 120 degrees Fahrenheit. On the left is called potential amount of water in the air. How much water the air can actually hold. Sometimes the air can hold lots of moisture, sometimes it can't, and it's relative to temperature. And that blue line indicates how much moisture the air can hold given a temperature. So, when we move from 0 degrees Fahrenheit to 20 degrees Fahrenheit, that red block shows how much more moisture the atmosphere can hold. Not a lot. In fact, there is a saying that says too cold to snow. And the reason why when it's 0 degrees, it doesn't snow is because there's almost no moisture in the air whatsoever. When it warms up to 20 degrees Fahrenheit, we're still below freezing, and there's not a lot of moisture the air can hold. Orange, we now move 20 degrees from 40 to 60. And we see that the atmosphere could hold more moisture at 40 degrees. Then we go 20 degrees from 80 to 100, and that green box shows that the ability of the atmosphere to hold moisture increases exponentially, tremendously. Each one of these blocks is an increase in temperature of 20 degrees Fahrenheit. The green box is so huge because that's the warmest. So as the air becomes warmer, it can hold more moisture. And this graph shows that, right? It's physics. It as long as the is as physics of the atmosphere doesn't change, the warmer it gets, the more moisture our atmosphere can hold. And so what's happening is we continue to put greenhouse gas in the atmosphere. We continue to see the global temperatures rise. And as the global temperatures rise, our atmosphere can hold more moisture. We even measure moisture in the atmosphere. Again, these are observations. And so we start in 1940 and we go up to 2023. Each dot is a year, and we can see the long-term trend of increasing moisture in atmosphere. We now have rivers of moisture in atmosphere. I've probably heard of them, atmospheric rivers, because there's so much moisture going into the atmosphere. So the ability, so not only does the atmosphere have a greater ability to hold moisture, it has more energy. And so that energy is going into evaporating water out of the soil, out of rivers, out of lakes, and evaporating into the atmosphere. And because the atmosphere is warmer, it can hold a lot more moisture. And so we're getting these record droughts around the world. A term that just came out in March in the scientific journals is called atmospheric thirst. By increasing the global temperatures and increasing the ability to hold moisture and giving the atmosphere more moisture, we've made the atmosphere thirstier, and it's got more power to suck moisture out of the earth. It's like getting a new vacuum engine every year and a new vacuum bag. You've got more power to pull dust out of your carpets, and you've got more room to store that dust. That's what's happening in our atmosphere. Where I live in the Salem, Swampscott, Lynn, Marblehead area. And last year we had a drought. The atmosphere was very thirsty, and we had lots of fires. This is looking over Lynn, fires behind Lynn. Speaking of fire, so again, this is a graph of observations. The red are droughts, global land area that's in extreme drought, 6 months or more. The orange is 3 months. The gray is 1 month. The black box shows where I showed you around the 1970s where I felt like the climate, that's where the change was happening. And we can see, based on these observations, that the world is getting drier. The atmosphere is becoming more thirsty, and we're seeing more extended droughts. You might notice that the price of coffee is rising because of the terrible droughts in Brazil. And fire. So a thirsty atmosphere not only draws water out of soil, out of lakes, it also draws the water out of vegetation. And Los Angeles went 2 years with extensive rainfall, extra rainfall than normal, and a lot of vegetation grew. And then they went through a severe drought. And that thirsty atmosphere made everything dry. And the burning of LA was almost apocalyptic. Last year was the first year where fire created more deforestation than agricultural expansion, as far as we know, through research. Our world is on fire because of the atmospheric thirst, because of the warming of the atmosphere, because of the greenhouse gases. Floods. If you've been attuned to the news recently, right, we've had a lot of floods here. This is last year. Uh, these just phenomenal floods. And one thing you'll notice when you read about floods now is people say, I've never seen anything like it. That's because we haven't had an atmosphere that could create such flooding before. But this warm atmosphere that has so much water in it, when it lets it go, creates this incredible flooding. In Spain, that street. And Vermont, Sutton, Vermont, July 10, 23, they got hit with flooding. July 10, 24, they got hit with flooding. July 10, 25, they got hit with massive flooding. Here, so not only is the atmosphere having more moisture in it and creating flooding, but when it leaves, it tends to leave in heavier rainstorms than in the past. And so you might see this lightly grayed out area. It's called the base period, right? We talked about a base period earlier. So the base period here is from 1960 to 1990. Then we've got a break, and then we've got everything since, I'm not quite sure, 94, since 94. And we can see that we're getting heavier rainfalls. On the left-hand side is rainfall intensity. Oh, they said the other day in New York City that for 15 minutes they had more than 4 inches of rain per hour, which is phenomenal amount of rain coming out of the atmosphere. Where I live, we get an average of 4 inches in a month. Not to spend much time on this, but natural disasters, which a lot of climate driven, are driving our home insurance up. That is becoming a problem. All right, like I said, like never before. About I'm gonna say I think 2021, I started working on this project with Jia Chang Tu, who was a master's student of mine at Salem State, and her thesis was looking at flooding in Shanghai. And at the time, we were gonna model 1 in 100, 1 in 250, 1 in 500, 1 in 1,000 floods. And I thought, 1 in 1,000, that's kind of crazy, but okay. And then we also are modeling 1 in 5,000 year floods. And I thought that was kind of crazy, but now we're seeing every year we're seeing 1 in 1,000 floods. And the one thing about that graph we saw of the exponential ability of the atmosphere to hold moisture is we are rapidly seeing some pretty horrific flooding because of that. All right. Um, so uh, yeah, I'll talk about New England. Um, so I published a paper, and I published it with my son Joshua. And overall warming with reduced seasonality, temperature change in New England, USA, 1900 to 2020. COVID came, and two of my kids came home from college, and I suggested, hey, let's do a data project. And one of my sons said, yeah, let's do it. And so we looked at temperature in New England, and we were so amazed at the change that happened that we decided to publish this paper in the journal Climate. And we looked at these different weather stations across New England. And these weather stations have been the data's been checked. They've been collecting data throughout the time period. Anyway, there's a lot of restrictions. There's a lot more weather stations, but we use the best. And what turned out is that between 1900 and 2020, minimum temperatures in New England were warming the fastest. And that's another reason why we're not feeling climate change as much, is because the minimum temperatures are warming quickly, not the maximum temperatures. If the maximum temperatures were warming quickly, we'd feel it faster. But those minimum temperatures in the winter is warming faster than any of the other seasons. And here's a graph of the blue line is global data, and the orange line is New England data, our data. And those black up and down lines are those confidence intervals or uncertainty. And because we don't have as many data sites as the global one does, we've got more uncertainty. But when this black bar does not cross the black bar of the other line, it means they are significantly different from each other. And New England is warming significantly faster than the rest of the world. In fact, we are accelerating in our warmth faster than the world. And I just finished this this morning, actually, a new data set that takes me up to 2024. And again, the blue line is global data, and the orange brownish line is New England. And for the last 5 years, New England has not only continued in its warming, but has accelerated in its warming. And so here is an interesting. This is New England temperature, and I normalized it to 1975, that period where I said the world was changing. The blue line on top is minimum, the orange line in the middle is average, and the green line is maximum. And this shows that minimum temperatures in New England are rising faster than maximum temperatures. And so we're really not feeling the change as much. Although with the minimum temperatures rising so quickly and winter warming, we are losing snow cover. I'll get to that in a second. Anyway, our results got on the front page of the Globe, and that was a fun project to do with my son Joshua. And there's a better picture of me instead of the party hat. Why are we warming so much? Well, certainly it is the atmosphere itself with the greenhouse effect, but also the waters just off of New England are warming up faster than most of the waters around the world. The Gulf Stream, which brings warm tropical water along our coast and goes over to Europe, is pushing further to the north. And a lot of that tropical water is coming into the Gulf of Maine. And so we're getting this warming effect. Also, some atmospheric effects as well, but not going to go into the details of that. All right, I mentioned snow cover. So with a graduate student of mine a few years ago, we used satellites, and the satellites looked at the temperature of the surface of the Earth, looked at the vegetation, and also looked at, is there snow or is there not snow on the ground? We didn't measure the depth of snow, we just measured whether there was snow or not, because deep snow and shallow snow both reflect solar radiation back to space. No snow, that energy gets absorbed by the Earth. When there's snow on the ground, a lot of solar radiation gets reflected back to space. When there's not snow on the ground, most of it gets absorbed and turned into heat. Our study concluded that snow cover in northeastern North America was disappearing 12 times faster than increasing. Sure, a couple places it's increasing, but it's mostly decreasing. And there was a very strong relationship between snow cover and increasing land temperature. As snow cover disappeared, temperature increased. As snow cover increased, temperature decreased. And so this research showed the relationship between snow cover and temperature in our part of the world. Then I looked at the entire world of snow cover and discovered that snow cover is disappearing around the world. In 22 years, more than 5% of snow cover has disappeared around the world. And there's various distinct regions in the world called hotspots of snow cover decline. And one of them is in southern New England. In central eastern Massachusetts down towards New York into New Jersey is an area that is losing snow cover. The red is faster than 95% of the rest of the world that's losing snow cover, and the pink is top 10%. So one other reason why New England is warming is because we're losing snow cover and the sunlight is absorbing and not reflecting. Here's an image. This is a satellite image. This is the data I use, and the whiter it is, the The more snow there is, the darker it is, the less snow there is. Here's Massachusetts down here. There's Vermont, New Hampshire, Maine. And we're right at the kind of the edge of the snow in North America. And so what's happening is this edge of snow is melting back. And in fact, I finished this graph today. And this is New England. Maine is up here, Massachusetts, Connecticut, Rhode Island, Vermont, New Hampshire. The red is areas between 2000 and 2024 where 40% of snow cover disappeared. The pink is 30 to 40. Anyway, you can see that New England snow is disappearing from the southern side up to the north, and almost the entire region is losing at least a little bit of snow cover over the past 2 decades. This is my only slide of this. I saw this on an Alaska page, and data that I use to understand snow cover and stuff is disappearing. Right now, our government is removing data about the climate. Anyway, that's my only talk on that. Precipitation of New England. I'm getting near the end. Overall, it's been increasing. We've been getting heavier rainfall, more erosion, less infiltration. More of it's increasing in the wintertime. We're getting less snow and more rain. You know, I discovered that in the winter in New England, it is 6 degrees warmer in the minimum. And so when it is 34 degrees and raining, 40 years ago, it was 28 degrees and snowing. So by that minimum temperature warming up, we're getting less and less snow and more rain in the wintertime. And we're getting these whiplashes from dry to wet to hot to cold, a greater variations happening. Summers are getting hotter, similar precipitation, and so that thirsty atmosphere is creating more stress on the physical environment. And if you're a gardener, a birder, a walker, you've probably noticed this summer in some of these extreme heat events that it is affecting the plant and animal life where we live. Here's a graph of increased precipitation. The bluer the color, the more precipitation, the browner, the less precipitation. Our southwest, Arizona, Utah, Colorado, New Mexico, Nevada is in a serious drought, major drought. And we're getting more water. So our future. A student once said to me recently, like, why are scientists worried about climate change now all of a sudden? Well, we've been worried about it for a long time. In fact, the first published piece about the calculation of global warming from human CO2 emissions was made in 1896. It's not a new thing in science. In 1965, the environmental report noted by LBJ in the White House talked about climate change concerns. Jim Hansen in 1988, NASA's top climate scientist, testified to Congress that scientists were 99% sure that the world was warming and it was being driven by human activity and the use of fossil fuels. It's not new. We've known this for a long time. Our future, and you can, I'm going to show you the observations, and you can figure out what you think the future is going to be. We are continuing to put greenhouse gases in the atmosphere. In fact, our current policy where we in the United States are abandoning alternative energy like solar and wind and pushing the accelerator on fossil fuels, we are increasing the amount of greenhouse gases in our atmosphere, which is increasing the global temperature, which is increasing the ability to hold moisture, which leads to droughts and floods. And so you can imagine what our future will be like. World is warming, will continue to warm until we reach net zero. And we are quickly warming. Stopping climate change is no longer just an individual effort. It requires society to prioritize reducing greenhouse gases, especially in the infrastructure we create to live in. Jimmy Carter put solar panels on the White House. Americans invented photovoltaic solar panels to change sunlight into electricity. We had a vibrant solar panel industry in the 70s. We've got the knowledge, we've got the technology, we've got the wealth to stop using fossil fuels and use alternative energy and stop putting greenhouse gas in the atmosphere. We just lack the political will. That I should say, was opinion. Everything else prior up to that were observations, and were science about climate change. And my opinion is that we've got the ability to not have that future. Very quickly, scientists wanted us to stay below 1.5 degrees Celsius, and for more than so an average of 3 years at 1.5 degrees Celsius or more. We used to think it was coming at 2045. Last year, actually, we passed the 1.5 degrees Celsius. It's coming faster than we expected. At 1.5 degrees Celsius, we will begin to see catastrophic events, right? The burning of LA. Someone on this call is from, I think, Alberta. You know very well the fires that are happening up there as well. Catastrophic. And the flooding that happened in Texas and in New York is catastrophic. We're going to see more of it because of the atmospheric ability to hold moisture. Net zero, everybody's trying to get to net zero, which means not putting greenhouse gas in the atmosphere. And Massachusetts has got, and all the New England states have resiliency plans about how to do it. We know how to do it. It's not just rising temperature. There's a lot of issues. My university, very briefly, we have a very strong sustainability Salem State University program. We're pledged to go carbon neutral by 2050. We are actively decarbonizing our campus. We've divested from fossil fuels. We have solar panels on many of our buildings. We have LEED certified buildings. We have geothermal for our library, and that is how we are going to, one of the main ways we're going to decarbonize our campus. Heavily recycling, composting, e-bikes, e-cars. My department trains individuals in understanding the climate using geospatial technologies like drones and satellite imagery to monitor sea level rise, climate change. We have mapping exhibitions that we take on the road. One of my colleagues, Marcos Luna, is involved in climate and equity issues as well. So I think this is my final slide. Our future world is arriving now. Our climate, which has been relatively stable for a long time, past 8,000 years or so, has changed. We are at a point of change. We are going from a world of climate stability, certainty, to one of instability, uncertainty. We've known for a long time where you can plant corn, and it's going to get the rain that it needs. It's going to get the sunshine that it's going to need. We are beginning to not be so certain of that. We are because of climate change, because of the warming, we're entering a world of instability, and the driving force is the continuous production of greenhouse gases. Sure, there are a number of reasons, but the main one is our burning of fossil fuels. And it's going to continue to warm the planet, and it's going to continue to let our atmosphere hold more moisture, make our atmosphere more thirsty. It's in our hands how hot the future will be. And so I hope from this talk you have a better understanding of why our world is getting wetter and drier. And I think Robert was going to make some comments about the comments. read off some questions. We've got a little bit of time left. And
Here I
so
am, Stephen. Yep. So, folks, let's give Stephen a big virtual round of applause for a great presentation. And let's take approximately 10 minutes of questions. Stephen, do you mind staying until 8:05?
I don't mind at all.
All right.
In fact, I even
Okay.
put up my email address in case
Yeah.
somebody needs to contact me.
Yeah. And I'll include it in the follow up email. So, for anyone who has to drop off, I will include the recording and Stephen's email in a follow up email later tonight. Okay. First up is Carla. Is there a correlation between the many trees being cut down and the many poisons people are using on their lawns? Are there any correlations between those two things and climate change? So trees getting
Um,
cut down and poisons being used on lawns.
yeah, the you know the I don't know of a correlation between poison being used on lawns and climate change. Um, and yeah, it's crazy to put poison in our environment. And trees and climate change. Yeah, trees are getting stressed. And so there is some die off of trees due to stress from heat, from dry conditions, from weather whiplash as well. I hope that answers the question.
I think it does. Nancy asks, does the population increase have an effect on the temperature?
So, population increase has effect on temperature in that everybody needs food, everybody needs clothes, everybody needs housing, and through our economic activity, we create greenhouse gases. Some people, like people in Bangladesh, the Bangladesh would have to have a population of over 1 billion to produce as much CO2 as the United States produces. So individual populations they're not equal. And just our heat of individual humans, that does not have that much of effect on the warming of the world.
Shane asks, what is the most important thing that can be done to get back on track?
So for me, the most so people need to figure out what their niche is or their stick is. For me, one of the most important things for me to do is try to educate about the science of climate change so people can make a vote with educated understanding and do stuff. Someone who's involved in politics, maybe the best thing they can do is sway politicians to be concerned about climate. Or you've got a big friend group, and just talking about climate change and making people aware of it is one thing you can do. So every individual has some sort of connection that you can maximize with. So that's my answer to that.
Jason asks, when you teach students about climate change, what steps do you take to reduce their climate anxiety?
That's a great question. Uh, you know, um, I was a professor for 30 years. I still teach climate change online, but um, I have seen an increase in overall anxiety for sure with young people. And I think there's two things I think to reduce the anxiety. One is to have a better understanding of what's happening, and two, maybe there's three things. But two is you can't take it personally. You are not the cause. You individually are not the cause. You are not gonna save the world also. So don't have the anxiety that you're causing the problem. And do something what you can, right? Like I said, if talk to friends about it. People may not. That's a lot of scientists say we need to talk about it. We need to let people know that we're all concerned about it. And so I tell my students to do what you can, and like I answered that other one, where you can. But don't take it personally and understand it. All right, how was
Okay.
that?
Yep. Yep. An anonymous attendee. So there's several questions about, climate deniers, and even within the science community. So an anonymous attendee writes, there are some scientists, and they put that in quotes, who claim that climate change is not a real issue to worry about. It's just part of the Earth's normal cycle. What do you say to those scientists?
One thing I've noticed, and I often give lectures in Salem to what's called the Explorers Club. It's a retiree club, and there's some people who there's one person who's a Ph.D. scientist, and refuses to believe that carbon dioxide absorbs thermal energy, even though there are thousands of scientific experiments that show that. So there is a certain, and I don't know if it's politics or what drives that. So there's a certain percentage of our population, even PhD scientists, who refuse, for some reason, to believe the science. And the natural changes, and I didn't go detail in this lecture, but I do have another lecture where I talk about what are the various natural effects that change climate. Like I pointed out earlier, the changing orbit and tilt of the Earth. There's a variety of things. Those natural things have been totally accounted for. And there is overwhelming evidence that it's those greenhouse gases in our atmosphere that are causing the climate to change, and the fringe deniers. It doesn't matter. Unfortunately, some of them are very powerful and can sway people. But that's my answer to that.
So, somewhat related question from Paulie, who notes, will climate change research be crippled by the changes at the National Oceanic and Atmospheric Administration? And will your research be affected?
So my research won't be so affected except if data becomes unavailable. I get a lot of my data through the federal government and state governments. Yeah, right now, so many climate scientists are being let go. So many climate studies are being unfunded. It This is opinion. We are our current policies are, to a scientist, insanity, suicidal. You saw those graphs that I explained and what's happening, and getting rid of solar and wind and disincentivizing that and incentivizing the use of fossil fuels is in my view crazy. And to cut, we want to be able to see the future to stop that data so we don't know what the future is going to hold. That's like not warning that camp in Texas about what's going to happen. All right, I'm going to get off my soapbox on that question.
I think that you're fine getting on your soapbox for a topic like this. No worries. So let's see here. Cindy asks, as of last year, the Gulf of Maine was colder than it had been in the past decade. Do you think that will then influence the temperature? How quickly would you expect to see a connection?
Yeah, that's a great point. I would expect to see some of that within, right? The air is blowing off the ocean, and certainly coastal areas, I would expect to experience it fairly soon. And again, on all those graphs, I showed you how things go up and down, up and down, up and down, up and down. And so we're going to have periods where things cool down, and then they heat up and heat up again, and then they cool down. And when they cool down, they tend not to cool as much as they were a few decades ago. So I would expect to see that kind of variability, and I certainly do think it would have an effect on certainly coastal temperatures.
So John says, you made an interesting point about connecting droughts to a rise in coffee prices. How can we mobilize people to make these real, tangential connections so that climate change doesn't feel like this distant, not my problem type of phenomenon?
Great question. And I wish I had a great answer for it, but again, just talking about it, right? Making people aware that that's happening, uh, and anybody who has ways of reaching more people, that's how we can do it. And you know what? It's it's not that that information is not out there. It is out there. When I did a sabbatical in England, and when I was there, they said concerning understanding our world and news, Americans are the most entertained and the least informed. And I often say, does anybody know that Taylor Swift has a football player as a boyfriend? And almost everybody knows that. But do you know about the war that's going on in South Sudan, or the major drought in the Amazon, which is affecting coffee production? Yeah, our again, I'm on my soapbox here, but our media, we tend to be entertained more than informed, and I wish we were informed more, and I hope that'll change.
We're going
Roundabout
to take,
answer.
that's okay. We're going to take a few more questions. Jane asks, what is the relative contribution to greenhouse effects of CO2 from burning fossil fuels compared to methane from beef and other meat production?
All right. So that's another great question. I don't know the exact statistics, but um, carbon dioxide is a greenhouse gas and methane is a greenhouse gas. And methane is like 60 to 80 times more powerful than carbon dioxide. However, carbon dioxide hangs out in the atmosphere for about 1,000 years naturally, where methane stays in the atmosphere for decades and will come out of the atmosphere faster. So we've been focusing on carbon dioxide because of its longevity. However, because methane is stronger and fast acting, there's now concern with scientists about that which the person was bringing up about cattle. You know, we often leave our oil wells uncapped, and lots of methane is escaping and not being kept. So there's a lot of methane going in the atmosphere from a variety of sources, and it's a concern because of its power and its short-term action. I hope that is in the ballpark of answering.
I think so. Thomas asks, how was decreasing and even eliminating CFCs by corporations to protect the ozone layer accomplished relatively so easily and so impressively quickly?
That's another great question. Yeah. So CFCs, these chlorofluorocarbons that were discovered by a NASA scientist to be creating this hole in the ozone layer over Antarctica. And ozone protects us from ultraviolet radiation. And so as the ozone layer was disappearing, more ultraviolet radiation was making it to the Earth, and it could be deadly. We understood the science of it. And we had a thing called the Montreal Protocol, where countries came together. And those countries said, okay, the wealthy countries will phase out chlorofluorocarbons quickly, and they will innovate and they will come up with alternatives. And then in the future, less wealthy countries will have access to cheaper alternatives. And eventually we will stop putting CFCs, or well, not stop it, but minimize it tremendously. And it was successful because we knew the science, we agreed it was a problem, and wealthy countries stepped up to the plate and created a solution, and it's been stabilized. And we can do the same with climate change. It's a bigger problem though. All right.
We're in double overtime. Two more questions, and then we're going to wrap things up.
Okay.
Sandy asks, how does the melting ice caps and thus changing ocean salinity impact the cycle of evaporation and warming?
So, um, I don't know how that changes evaporation. However, the melting of the sea ice and the melting of Antarctica, melting of Greenland, and the melting of sea ice in the Arctic is cooling the water in many places, isolated cooling. However, it is making the Arctic more open than it used to be. And less ice means there's less reflection and there's more absorption. So there are some scientific models that are going to show changes in precipitation in northern Canada, northern Alaska, because of that melting of the sea ice and opening up the water available. The melting of the ice off of Greenland and making more fresh water and less saline water is slowing down the Gulf Stream and could actually even stop it, because what happens is by the time the Gulf Stream gets over towards Europe, it's cooled and it's salty, and the salt makes it sink, which keeps the currents going like a conveyor belt. Now that it's getting less salty and it's not sinking as fast, and so the conveyor belt is kind of slowing down. So that's the answer to that.
Final question goes to Dorothy. And Stephen, you can get back on your soapbox. Dorothy asks, do you have any idea how politicians on our side can improve their efforts? Senator Sheldon Whitehouse is a big champion, as is Ed Markey, among others. Any other approaches? So, how can we get the politicians on our side to improve their efforts?
Yeah, that's a difficult question. And what's amazing to me is back in the late 1980s, climate change, global warming was a huge issue. In fact, Time Magazine, 1988, Earth was Planet of the Year. George Bush in the White House had a plan to fight global warming. George Shultz, a Republican, came up with a carbon tax idea. And in the 1990s, early 90s, when Republicans were coming up with all kinds of ideas, and politicians were on the side of concern about climate warming, the fossil fuel industry started spending millions of dollars on disinformation and has been very successful. And money has swayed politicians against pushing for climate change. And I don't know. I don't know how to get them to swing the pendulum back the other direction. I try through education. I write to my senators, and I personally met and spoke with Markey about it when he was running for re-election. If you find the answer, if anybody finds the answer to that question, let me know.
So, Stephen, any last words for the audience before we wrap up?
Well, I want to thank everybody who stayed on, and most of you did, for joining me this evening. And I hope that I was able to clearly show the science of climate change and what's happening in our atmosphere, so you will understand. And I tell you, from now on, when you read about floods, you will see I've never seen anything like it written by people. And you yourself may experience floods that you've never seen before, or other events. And I do hope in all of you, in each way that we can, to try to solve this situation, because I really do believe we are headed for a very difficult future. I've got children I don't have grandchildren yet, but I plead you to help us solve this issue. All right, that's enough. Thank you. I'm
All
waving
right.
at you right now.
Yeah. So, folks, give Stephen a big virtual round of applause once more. For those watching live, look for an email later tonight with a link to the recording, as well as information about some other upcoming programs. And again, for those watching live, when you exit, please take 60 seconds or so and fill out the feedback survey that should pop up on your screen. So thank you all so much, and I hope everyone enjoys the rest of their evening. Thanks again, Stephen.
Thank you, Robert.